Okay, very, very short lecture today, very basic ideas. The first basic idea I want to get at is what is current and what is voltage? What's the difference between current and voltage? Actually, that's not even a fair question because they have absolutely nothing in common with each other. What's current? Yeah, it's a voltage difference will cause current flow. But what is current flow again?
The movement of charges.
It's the movement of charges, and specifically we talked about yesterday, it's the movement of the little electron holes, right?
Yeah.
So current moves from place to place. What about voltage? What is voltage?
Difference in potential energy.
It's like we originally defined it as the potential energy per charge, but remember the little battery thing we looked at with the little colored people?
Yeah.
Right, and remember how that worked and what a battery actually does?
Right.
It creates a voltage difference by taking charges from one side and then putting them all in the other side. So the high side, it has a whole bunch of charges all smushed together. So voltage is kind of a measure of how smushed together the charges are, whereas current is kind of a measure of how fast the charges are flowing. Does that make sense? All right, now, so voltage is potential energy per charge, and we did this awesome thing Mr. Torp came up with in regular physics with a toll booth analogy. Has anyone seen Mr. Torp's toll booth analogy before? It's really cool. It's like, all right, so you want to get cars down a road, and you get 400 cars down the road, and if you only have one toll booth, how many have to go through that one toll booth? 400, and if you put the toll booth and toll booth, right, in series with each other, how many cars have to go through each toll booth? 400 through each one, right? Now, if you're going to charge $10 total on this toll road, and you charge $5 on the first toll booth, how many do you have to charge on the second toll booth? $5 to charge a total of 10, right? And so the analogy we used was the cars going down the road, that's the current, and the amount you're charging, well, that's the voltage drop, right? Or you could call the voltage the amount of money in the driver's pockets, right? So every toll booth drops the voltage or drops the amount of money that each driver has. So voltage is the energy or the money that the drivers have as they're going through the toll booths.
How much money do you have on you? $40. Okay, you owe me $20.
Right. Yeah, exactly. That is kind of how life works in many respects. Yes.
Would you say voltage is like the gas in the car?
Yeah, you could say it's like the gas in the car, I guess.
So it doesn't only lose voltage at the toll booth, but as it goes the distance?
Yeah, so that's where the gas analogy kind of breaks down a little bit. Yes, you do lose a very, very tiny amount of energy as you're driving through the wires. The vast majority of the energy that you're losing is when you drive through the resistors. Right? So
It's the resistor.
yeah.
What is it though?
What is it about the resistor that causes that to
No,
happen?
I'm asking in the analogy, what would it be?
Yeah, I see. I don't like that. I don't like that gas analogy that much for that reason because there's like.
No, the resistors, the toll.
Yeah, resistors are the toll booth. Makes sense,
Yeah.
Yeah, because it's like a gate.
But then voltage.
The money analogy works a little bit better because, in the wires you don't really lose much. If you think about it this way, how much resistance does a typical wire have?
Low.
Very, very little, right? That means that to get through the wire in real life, in a real circuit, to get through the wire, it takes very, very little voltage difference to drive a current, right? Right? If you want 1 amp of current, it's going to take, the voltage is going to drop very, very little to get 1 amp of current through. Whereas to get 1 amp of current through that resistor, it's going to take a lot of voltage difference from one side of the resistor to the other to drive the current through. That's why you lose the majority of your voltage across the resistors. And you might lose an unmeasurable amount across the wire, each wire. All right, and that's typically when if we've got time, we'll actually break out the real wires and the real voltmeters. And we'll measure across from one end of a wire to another in a typical circuit. What you're going to find is the voltage difference from one end of the wire to the other might be so small that the multimeter can't even pick it up.
Yeah, like if you're using a 10,000 ohm like resistor on something, it doesn't need to be that high. Wouldn't that just like almost completely stop the current flow?
Well, assuming you've got a current flow, even if you got like 2 amps of current flow, you might not measure any voltage drop across that wire at all. It's because it's so typically so small. There is a little bit because there would have to be to push the charges to create that electric field to push the charges, but it doesn't take very much electric field at all to push the charge through a wire. All right. Superconductors. You guys know what those are?
Yeah.
How much voltage difference? How much electric field does it take to push charges through a superconductor?
0.
Exactly 0.
But that's impossible, right?
No, it is possible. It happens.
requires it to be super cold.
Yeah, it's like superconductors are super cold too. So you never we haven't created any superconductors that can exist at room temperature as a superconductor.
So no one ever does it.
You do use superconductors in like Fermilab, right? But not for everyday use. We've got the basic idea of the difference between voltage and current, and that's awesome. So that brings us. We did a whole lot of problems last year with voltage and current, but this year we're going to take it and we're just going to take it up a tiny little step from where you were last year, and we're going to call it a day. Sound good? And here's the tiny little step. There's something called Kirchoff's laws. Have you guys heard of them?
Now we
No.
have.
All right. Kirchoff is this, I think he's Russian guy, 100 and something years ago, was looking at circuits and realized that 2 things have to be true for any circuit. First of all, let's say you had 3 wires meeting at one spot. And so I have it drawn here. That's the spot these 3 wires are meeting at. Wouldn't you agree that any current that comes into that spot has to leave that spot?
Yes.
Why?
Conservation.
Conservation of
Energy.
electrons, right? Or charge. It's not energy, it's actually charge.
What's the difference?
What's the difference between a thing and energy? One is a physical object. A charge is a physical object. So if you have 10 charges in, how many charges have to go out? 10. All right. So say you had 10 charges coming in this way and 2 went down this way. How many have to go this way? 8. Right? Does that make sense?
Yeah.
So Kirchoff said that the total amount in has to equal the total amount out. Make sense? All right, so that was his first law. It says Kirchoff's current law, also known as Kirchoff's node law. This is called a node. This is a nose, this is a node. And if you have a code, sometimes this becomes a node instead of a nose, right? So, node law. My node is code. Right.
Wasn't this taking too long?
Anyway. Yes, it's taking too long. Let's move on. All right, so Kirchoff's current laws is merely a restatement of the law of conservation of charge, which is one of the 4 fundamental laws of the universe. Kirchoff's voltage law is a little bit trickier to think about, but it goes like this. Let's say a charge started here with a certain amount of energy, right? Then it goes through the battery. What's the battery do to the charge's energy? It increases it, right? Because voltage is energy, right?
Yes.
So it gives the charge more money, right? Say $10 worth. And then as it goes around here, it loses $4. How much does it have to lose here? $6 of energy. Or in other words, if you gain 10 volts here, and you lose 4 volts across here, you got to lose 6 volts across here to get back to where you started, right?
Yeah.
So what was the total change in voltage for that whole loop that you drew? 0.
Gosh.
Oh, yeah.
Dang it.
Right? It's 0 volts. So if you start at one spot and you go all the way around a loop, you gain 10, you lose 4, you lose 6, so you're back down to 0 again.
So it's a matter of where you start.
Yeah, if you pick a starting point and you go around any loop in a circuit, even if it has more than one loop, from start to finish, the total voltage change must be 0. And that is a restatement of the law of conservation of energy, not charge. So the current law is about charge, the voltage law is about energy. Does that make sense? All right, so let's take a look at see how this is applied. Example, you've got a circuit. It's got 2 batteries in it. Has anyone done a 2-battery circuit before?
No.
No, because last year you only did 1 battery, right? Well, check this out.
Don't you just add that?
Let's start at this point. You go through this 10-volt battery, then you go through the first resistor, then you go through a 5-volt battery, then you go through the second resistor. If you were to draw a Kirchoff's voltage law equation for this, here's what the equation would look like. We pick a starting point. What's the first voltage we hit?
10.
Plus or minus 10?
Plus.
Plus 10. What's the next change in voltage going to be?
Current time.
The
Current times.
current times 2 ohms. Right? Because V equals I times R. Right? Now the current times, is that going to be a gain or a drop?
Drop.
Okay, so it would be plus 10 volts minus IR1 plus 5 volts minus IR2 equals 0. You got it?
Yeah.
So the equation looks like this. 10 volts minus I times 2 ohms plus 5 volts minus I times 3 ohms equals 0. Combine like terms, and you're left with current equals 1 amp. You see how we did that?
So if it loses a lot, it has to gain that same amount.
Exactly. If it loses 12, it's got to gain 12 in order to get back to 0 again. Okay, so that was a really simple one. Let's do a harder one with 2 batteries. All right. We've got a loop here, and we've got a loop here, and we got currents coming in. How many currents are we going to have to figure out to solve this whole circuit?
2.
3.
3. Because of when they come together after that.
This one is one current, this one is 1 current, and the current coming through here is a 3rd current. So how many unknowns do you have?
3.
3. If you have 3 unknowns, how many equations do you need?
3.
3 unknowns means 3 equations. What 3 equations are you going to draw?
I1 plus I2 equals I3.
I1 plus I2's got to be I3. That's your first equation. Your second equation comes from this loop.
10 volts minus 7.
And your third equation comes from this loop. You set it up, and you've got a system of 3 equations. Guess what you can do?
Substitute.
You can use substitute. You can use Gaussian elimination. You can plug it into your calculator, because you all have calculators that can solve systems of 3 or 4 or 5 or 7 equations. So today, what you're going to be doing is solving systems. There's one that has 7 equations. So don't bother trying to solve that by substitution, because it will take you about 20 pages. Yes?
For example 1, where you did the like terms, isn't it 10 volts plus 5 volts is 15, and then the other side would be,
That's you.
Oh, did I do that wrong?
isn't it 3 amps?
Yeah, wait, hold on. It looks like I have a math error. 10 volts, 5 volts, yep. I don't know why I can't add. Yeah, so that should be 15 volts equals I times 5. Did you guys catch that as you were looking at it?
Yeah.
Oops, sorry. Yeah, so this should be 3 amps, not 1 amp.
Okay.
Or, sorry, yeah, 3 amps. Okay, that's it. All right, let's get to work.